welcome you in the lecture series of random processes, detection and estimation. It is 29th lecture of this series. In the previous lecture, we have discussed the CRLB for transform parameter, CRLB for vector parameter case. In this lecture, we will discuss CRLB for vector parameter transformation and CRLB for general case. The outline of this lecture are Kramer-Rao lower bound for vector parameter and CRLB for vector parameter transformation. Then we will discuss CRLB for signal in white Gaussian noise and then CRLB for general Gaussian noise case. In the objective of this lecture, you will able to explain how the CRLB theorem is used for finding MVUE and how to find CRLB for signal in white Gaussian noise. And also you will able to explain how to find CRLB for general Gaussian case. Now first we will take the CRLB for vector parameter. There is one theorem related to this. Let PDF px theta satisfy the regularity condition, means expected value of del log e px theta by del theta is equal to 0 for all value of theta, where the expectation is taken with respect to px theta, then the covariance matrix of any unbiased estimator theta cap, it specify c theta cap minus I inverse theta, it will be greater than equal to 0. That is, matrix is positive semi-defined. The Fisher information matrix I theta, it is I theta II, it is equal to minus expected value of del square log e px theta by del theta I del theta j. The derivatives are evaluated at the true value of theta and the expectation is taken with respect to px theta. The unbiased estimator attains the bound, that is c theta cap is equal to I inverse theta if and only if the del log e px theta by del theta, it will be equal to I theta gx minus theta for some n-dimensional function g and for some n is to n matrix I. The estimator, which is MVUE estimator, is theta cap is equal to gx and its covariance matrix is I inverse theta. Now let us consider the CRLB for vector parameter transformation. Let alpha equal to g theta for g r dimensional function and c alpha cap minus del g theta by del theta I inverse theta into del g theta transpose by del theta greater than equal to 0. Here del g by del g theta by del theta, it is the Jacobian matrix and it will be equal to the matrix with del g1 theta by del theta 1, del g1 theta by del theta 2 up to del g1 theta by del theta p, del g2 theta by del theta 2, del g2 theta by del theta 2 and up to del g2 by 2 theta by del theta p, and it is del gr theta by del theta 1, del gr theta by del theta 2 and it is up to del gr theta by del p theta. It is R is to P matrix. And let us take one example. The observation is xn is equal to a plus omega n, where small n is 0, 1 to n minus 1. This is DC level in white Gaussian noise, where omega n is the white Gaussian noise process with variance of sigma square. Here a and sigma square are unknown. Estimate alpha is equal to a square by sigma square, which is SNR for single sample. This means you have to find the CRLB for signal to noise ratio. So from the previous question, we know the variance of A cap, it will be greater than or equal to sigma square by n, as we have solved in the previous question, in the previous lecture. And variance of sigma square cap, it is greater than or equal to 2 sigma is to the power 4 by n. Here theta is the transpose matrix of A and sigma square, and g theta, it will be theta 1 square by theta 2 square, it is equal to A square by sigma square. And from the previous example, the information, the Fisher information, it will be the matrix n by sigma square 0, 0, n by 2 sigmas to the power 4. Now the Jacobian means del g theta by del theta. It will be equal to the matrix del g theta by del theta 1 into del g theta by del theta 2, and it will be equal to del g theta by del A into del g theta by del sigma square, and because theta 1 is A and theta 2 is sigma square, so it will be equal to 2A by sigma square and minus A by sigma to the power 4. So we can write del g theta by del theta I inverse theta del g theta transpose by theta, it will be equal to the matrix with component 2A by sigma square and minus A by sigma to the power 4 into the matrix sigma square by n 0, 0, 2 sigma to the power 4 by n. This is the Fisher information matrix, and then 2A sigma square by and minus A by sigma is to the power 4. This is transpose of g theta, and this is g theta, and it is I inverse theta. So, and it will be equal to 4A square by n sigma square plus 2 A is to the power 4 by n sigma is to the power 4. Since alpha is a scalar, and it can be equal to 4 alpha plus 2 alpha square by n. Since alpha is a scalar, so variance of alpha cap, it will be greater than equal to 4 alpha plus 2 alpha square by n. It is CRLB. Now CRLB for signal in white Gaussian noise. Let the data set xn is equal to Sn theta plus omega n, where small n is from 0 to n minus 1, and omega n is the white Gaussian noise process, and here theta is the unknown parameter to be observed. The Fisher information theta, it will be I theta is equal to 1 by sigma square summation n0 to n minus 1 del Sn theta by del theta whole square, and the variance of theta cap, it will be greater than equal to sigma square divided by summation n0 to n minus 1 and whole square of del Sn theta by del theta. So this is bound emphasize the importance of the signal dependency on theta. Now let us take a look of the proof of these two. So the likelihood function is, px theta, it will be 1 by 2 pi to the power n by 2 into 1 by sigma to the power n by 2 into e to the power minus 1 by 2 sigma square summation n0 to n minus 1 and the whole square of xn minus Sn theta, and taking the log both sides, you will get log likelihood function log e px theta, it will be minus 1 by 2 log e 2 pi minus n by 2 log e sigma square minus 1 by 2 sigma square summation n0 to n minus 1 and the whole square of xn minus Sn theta. And taking the first derivative with respect to theta, you will get del log e px theta by del theta, and it will be equal to 1 by sigma square derivative of this, it is 1 by sigma square summation n0 to n minus 1 xn minus Sn theta into del Sn theta by del theta. And taking the second derivative, you will get del square log e px theta by del theta square, and it will be equal to 1 by sigma square summation n0 to n minus 1 xn minus Sn theta into del square Sn theta by del theta square minus whole square of del Sn theta by del theta. Now the expectation of this means expected value of del square log e px theta by del theta square, it will be equal to minus 1 by sigma square summation n0 to n minus 1 and the whole square of del s and theta by del theta. So here you know the Fisher information I theta. It will be negative of the expected value of second derivative log likelihood function. I theta will be equal to minus e del square log e p x theta by del theta square, and it will be equal to 1 by sigma square summation n0 to n minus 1 and the whole square of del s and theta by del theta. And the CRLB variance theta cap, it will be greater than equal to sigma square by summation n0 to n minus 1 whole square of del s and theta by del theta. We will go for the CRLB for the general Gaussian case. Let x is equal to normal random process with mean mu theta and variance c theta, where both the mean and covariance may depend on theta. Then the Fisher information matrix can be given as I theta ij. It will be equal to del mu theta by del theta I transpose c inverse theta into del mu theta by del theta j plus 1 by 2 trace of the square matrix c inverse theta del c theta by del theta del c inverse theta del c theta by del theta j. Here the trace of the square matrix means the sum of the diagonals of the square matrix. And the proof of this is very lengthy, so it is omitted here. And here del mu theta by del theta I, it is equal to the matrix del mu theta 1 by del theta I, del mu theta 2 by del theta I up to del mu theta n by del theta I. And del log e, determinant of the covariance matrix c theta by del theta I, it will be the trace of the square matrix c inverse theta del c theta by del theta I. Now del c theta by del theta I, having the matrix with the column elements with first row element are del c theta 1 1 by del theta I, del c theta 1 2 by del theta I up to del c theta 1 n by del theta I, and second row is del c theta 2 1 by del theta I, del c theta by del theta I 2 2, del c theta 2 n 2 by del theta I, and it is up to del c theta n1 divided by del theta I, del c theta n2 by del theta I, and it is del c theta n by del theta I. It is n2 n by n matrix. And for the scalar parameter case, in which the random process x is the normal random process with mean mu theta and covariance c theta, and I theta now reduced to del mu theta, the transpose of the matrix del mu theta by del theta c inverse theta del c theta by del theta plus 1 by 2 trace of the whole square of the matrix c inverse theta del c theta by del theta square. Now let us take one example. Xn is Sn theta plus omega n, where small n is 0 to n minus 1. Now where omega n is the white Gaussian noise process and theta is unknown parameter to be observed. You know the Fisher information of theta is I theta is equal to del transpose of the matrix del mu theta by del theta into c inverse theta into matrix del c theta by del theta plus 1 by 2 trace of the whole square of the matrix c inverse theta del c theta by del theta. And this term is 0 because c is independent of theta in this case. And so I theta will be equal to 1 by sigma square into transpose of the matrix del mu theta by del theta into the matrix del mu theta by del theta, and it can be equal to 1 by sigma square summation n0 to n minus 1 del mu theta n by del theta and whole square of this matrix, and it will be equal to 1 by sigma square summation n0 to n minus 1 and the whole square of the matrix, it will be equal to 1 by sigma square summation n0 to n minus 1 and whole square of del s n theta by del theta. Let us take one example. Xn is omega n, where n is from 0 to n minus 1, where omega n is the white Gaussian noise process with unknown variance theta is equal to sigma square. Covariance depend on theta, and you have to find the I sigma square Fisher information. So you know C sigma square is equal to I square sigma square I. Here I sigma square is equal to 1 by 2 trace of the square matrix of the whole square of the matrix C inverse sigma square del C sigma square by del sigma square, and it will be equal to 1 by 2 trace of the square matrix and the whole square of the matrix 1 by sigma square I, and it will be 1 by 2 trace matrix 1 by I by sigma is to the power this will be sigma is to the power 4. Yes, this is sigma is to the power 4 into I, and it will be equal to n by 2 sigma is to the power 4. We can apply the theory of CRLB for several signal processing problems of interest like range estimation in sonar radar robotics, frequency estimation in sonar radar spectrometer, bearing estimation in sonar radar, and fourth is auto-regressive parameter estimation in speech. And let us take one example. The observed data is xn is equal to a cos 2 pi f naught n plus 5 plus omega n, where omega n is small n is from 0 to n minus 1, and it will be I can write it as equal to s n theta plus a omega, where theta is having the component a, f naught and phi. So theta is the transpose of the matrix A, f naught phi, where a greater than 0, f naught is between 0 to 1 by 2 and phi is from minus pi to pi. In this example, determine the CRLB for the estimation of the amplitude A, frequency f naught and the phase phi of the sinusoidal in presence of white Gaussian noise process. Since there are multiple parameters are unknown, the vector case of CRLB is required here. The covariance matrix C is sigma square I does not depend on theta. So I theta ij, it will be equal to the transpose of the matrix del mu theta by del theta I into 1 by sigma square I del mu theta by del theta j, and it will be equal to 1 by sigma square summation n0 to n minus 1 del s n theta by del theta I into del s n theta by del theta j. For evaluating the CRLB, it is assumed that f naught is not close to 0 or 1 by 2, which allow us to make certain assumptions, means 1 by n is to the power I plus 1 summation n0 to n minus 1 n is to the power I sine 4 pi f naught n plus 2 phi, it will be approximately 0, and 1 by n is to the power I plus 1 summation n0 to n minus 1 n is to the power I cos 4 pi f naught n plus 2 phi, it will be also approximately 0 for I 0 1 2, and let alpha is 2 pi f naught n plus phi, then in this case I theta 1 1, it will be 1 by sigma square summation n0 to n minus 1 cos square alpha, and it will be equal to 1 by sigma square summation n0 to n minus 1 1 by 2 plus 1 by 2 cos 2 alpha, and it will be approximately equal to n by 2 sigma square, and I theta 1 2, it will be minus 1 by sigma square summation n0 to n minus 1 a 2 pi n cos alpha sin alpha, and it will be equal to minus pi a by sigma square summation n0 to n minus 1 n sin 2 alpha, and it will be approximately equal to 0, and I theta 1 3, it will be minus 1 by sigma square summation n0 to n minus 1 a cos alpha sin alpha, and it will be equal to a by 2 sigma square summation n0 to n minus 1 sin 2 alpha, and it will be approximately equal to 0, and I theta 2 2, it will be equal to 1 by sigma square summation n0 to n minus 1 a square 2 pi n whole square sin square alpha, and it will be equal to 2 pi a square by sigma square summation n0 to n minus 1 n square 1 by 2 minus 1 by 2 cos 2 alpha, and it will be approximately equal to 2 pi a whole square by 2 sigma square summation n0 to n minus 1 n square, and I theta 2 3, it will be 1 by sigma square summation n0 to n minus 1 a square 2 pi n sin square alpha, and it will be approximately equal to pi a square by sigma square summation n0 to n minus 1 n, and I theta 3 3, it will be 1 by sigma square summation n0 to n minus 1 a square sin square alpha, and it will be approximately equal to n a square by 2 sigma square. So the Fisher information matrix, it will be all these components, it will be 1 by sigma square n by 2 0 0 0 2 a square pi square summation n0 to n minus 1 n square pi a square summation n0 to n minus 1 n 0 pi a square summation n0 to n minus 1 n n a square by 2, and the variance will be the inverse of this matrix. So the variance of a cap greater than equal to 2 pi square by n, and variance of f naught cap, it will be greater than equal to 12 by 2 pi whole square eta n into n square minus 1, and variance of phi cap, it will be greater than equal to 2 n minus 1 upon eta n into n plus 1. Here eta is a square by 2 sigma square is the SNR. Frequency estimation of a sinusoidal is of interest, and the CRLB for the frequency decreases as the SNR increases and decreases as 1 by n to the power 3. So it is quite sensitive to data record length. Here, so far in this lecture, we have discussed about CRLB for vector parameter transformation, CRLB for signal in white Gaussian noise, and CRLB for general Gaussian noise case, and CRLB for general Gaussian case. It was a 29th lecture of the lecture series of random processes detection and estimation. To find MVUE is a difficult task. We can easily determine MVUE using linear model, and about which we will discuss in the next lecture. Till then, thanks for listening this lecture. Thank you.